give us a talk about. Oh, cool. Oh, so today we have Arcelia Ruiz to talk about all sorts of really wonderful things. So Arcelia is a grad student at UC Santa Cruz, working with marine clay right now, finishing up and past the slightly terrifying and maybe hopefully a little bit exciting process of applying for postdocs.
Hopefully it's getting better.
Including applying to come here with the Craig Fellowship, so we'll see, fingers crossed. Arcelia is you're an NSF graduate research fellow. You're also an LSST data science fellow, and you have a extraordinarily useful website for people who are like looking for resources for applying for things. And so check it out. And Arcelia also very kindly offered to kind of chat about career stuff with anybody who's interested here as well. So I think you're still kind of run through the rest of the afternoon.
Yeah.
All right. Well, thank you so much. Take it away.
Thank you. Yeah, thank you for the nice introduction. Yes, you already introduced me, so I have to do it again. I'm excited to be here. I've never been to Boulder, but I already, like I said earlier, I'm being sold by this view. So I'm very happy and excited to be here tomorrow as well. So yeah, the work that I will present is all falling under the same theme of using a planetary systems debris disk, as shown here, to understand how the planetary orbits have evolved over time. And you can do that by looking at how the structure of the debris disk is changing and how the planet's orbits are changing as well by either colliding or interacting with each other, the planets, or the planets interacting with the debris disk. So the debris disk is what I'm showing here, which is a disk that is left over after planets have mostly been fully formed. So this is not the protoplanetary disk. The gas has mostly dissipated, and there's a lot of dust around in the young disks. And there's also a lot of planetesimals, as you see with the rock-like things. And these planetesimals will span various size distributions. And as you see with this collision here, there's a lot of dust being regenerated over and over again. And so the young systems have a lot of dust, but over time, they can get blown out. But if there's a lot of dust, then that tells you something about what is currently happening in that system. In our solar system, we have various debris disks, but the one that I'm going to talk about today is the Kuiper Belt, which is shown here. They are icy objects that are beyond Neptune, and we'll either call this area the Kuiper Belt or the Transneptunian region. Depending on who you're talking to, we might use different things. So I might say Kuiper Belt object or Transneptunian object, which is a KBO or TNO. I have slightly started saying TNO more, but on days when I'm feeling, a little excited, I might say KBO. But anyway, so we have this belt, and they have various size distribution. The objects have various size distributions, and also are composed of different material, and they might look differently as well. And Pluto is that yellow orbit. It's part of the Kuiper Belt. As we all know, it was demoted from being a planet because it's slightly inclined and it crosses Neptune's orbit. So now it can be our favorite Kuiper Belt object instead of being our favorite planet. Yeah.
Is that an LSST impression or is that real?
The inclination itself?
No, the Kuiper Belt.
Oh no, this is an artist impression. Yeah, sorry, this is not the actual data. But we do think that there is a lot of material in all sizes, but we wouldn't actually be able to observe this much now. And so, like I said, there are various, there's a variety of orbital distribution in the Kuiper Belt, and that is what helps us understand what kind of planetary evolution occurred in our solar system billions of years ago. So the work that I do is in understanding what happened billions of years ago, and by looking at the structure today. So you don't have to understand this plot fully yet. I will go more into detail later. But what I want you to see is that in this space of 7 major axes, so the further you are from the star, that way. This is eccentricity, so how elliptical, the higher you are, more circular, and then inclination. Just by looking at it, it's color-coded as well, so that helps. There's clearly structure, right? You see objects in certain 7 major axes, some are clumping up in a certain region, and a disk extending that way. And so this tells us that this didn't happen randomly. It's not just by chance, but some kind of evolution caused the structure to look this way. And that's what I'll talk about in part 1 of the talk. And then in part 2, I'm going to talk about modeling the eumic debris disk, which is not shown here yet. That's a surprise for the end. But what I want you to see here is that in this collage of extrasolar debris disks, you can see a variety of structure. We see gaps, we see narrow rings, wide ring, warps in this one, and then clumps and other stuff. And so this type of structure gives you hints as to, well, maybe a planet is sculpting it. Is a planet within the gap? Is a planet causing clumps in the disk to show up? And then that's why we see one big one here. Is there an inclined planet? And that's why there's a warp, and so on. And sometimes, actually, it's not even a planet. Sometimes the self-gravity of the disk is enough to create some of the structure as well. But what I want you to get from this figure is that the debris disks are a very exciting thing to study. And these are young disks, right? There's not a lot of dust in the older disks. So in our solar system, our debris disk would not be observed from alien civilizations with the same technology that we have today. We would need a lot of dust to actually be able to observe it. And so they're exciting to understand, well, what is happening in that system now that could have happened in our solar system billions of years ago. And the big picture motivation for why I think this is very exciting is because ultimately I'm trying to understand, why is our solar system unique? Why is it that we have a habitable Earth? Our solar system architecture is unique in how the planets are distributed in space and the sizes that they have as well. And maybe it's because something in our early solar system, like a chaotic evolution in our early solar system occurred, whereas that hasn't occurred in other systems, or we just haven't found it yet. And so I want to know what happens during the teenage years of the system and what is going on in that life style of the teenage planetary system that then can change its trajectory later on. As we know, teenagers can be, volatile. They can change their trajectory in life later. And so who knows what can happen then? Sorry, I'm going to be silly for a second because I used ChatGPT to give me a nice image for a teenage planetary system. This is a dream AI generator, which is more cute. And this is the one that it gave me. But it was too angsty. So I was like, let me try it again. And then it just got creepy.
Oh, gosh.
So maybe one day I'll do my own image to tell the full picture of what I'm researching here. But anyway, I hope that helps you understand what is the overall picture, the overall motivation for why this work is interesting. So yeah, part 1 will be the solar system evolution, and then part 2 will be in looking at planet disk interactions in the eumic debris disk. So one well-modeled or well-studied model of the solar system is a gravitational upheaval. You might know it as the Nice model. The Nice model was the original version, and it has gone through many different forms. So I will just stick to gravitational upheaval at this point. And I'm going to show you a GIF of what the overall picture is of such a model. There are many details that I won't go into, but what I want you to see is that it's a very chaotic, very violent upheaval. So what you see here is a top-down view of a supposed solar system, many in the really early stages. Here there are 5 giant planets, which we can ignore for now. That's one of the models that is proposed. But the point is that the planets are going to interact with each other in a way that scatters their orbit. And you'll see that the green, which are the planetesimals, will get scattered outward. It should start soon, in a very chaotic way. And then all of a sudden, that nice, simple coplanar disk is long gone. What is it? 30 million years later. And so such a model, as you can assume, is going to really affect how the objects are distributed now in this day, right? And so part of this work is, well, can we compare what this model does to the structure we have today to be able to constrain, can this model have occurred or not? And there's a bunch of work for this model. It does a really good job at explaining the excited orbits or high inclined orbits of Kuiper belt objects, but it also doesn't explain everything. And so there's still a lot of work to be done in figuring out how much of this model actually affected the solar system, and maybe other models are also the reason why we have the structure we have today. So another important thing about this model is that it's very complicated to run. So most of my work is Nbody simulations, and this is a very chaotic system. What I mean by that is that if you change your initial conditions even slightly, okay, to the 25th decimal point, you're gonna get a completely different final configuration. And that makes it difficult because it's gonna become very computationally expensive to run thousands of these models, when really what I want is 100 models that qualitatively match the solar system at the end. But instead, I get one that qualitatively matches the solar system after running hundreds. And I will show you how that exactly happens. So this is a simulation that I ran using parameters from a well-studied NICE model paper. And I'm like, I did the same exact thing that they did. I think I did. But actually, just those small changes that I don't know about that they did in their paper will create a completely different final scenario. So here I ran this for 5 million years. And as a first-year grad student, naively, I was like, oh, great, I'm done. This is all I needed to do. But actually, you run it slightly further, and Neptune gets like ejected from the system. And so you change them slightly, and this happens. That's Neptune that goes to 200 or so AU. Change it again, and now they're at 60,000 AU. I guess it's a hyperbolic orbit at that point, because negative doesn't make sense, right? But and then again, you change it slightly, and again, it just doesn't work out. And so the work that I'm going to present is motivated by this computational expense. It's very infeasible to actually run hundreds of these simulations to be able to compare to the observations we have today. So I mentioned that I would go back to this plot later. One of the important configurations in the structure of the Kuiper belt are these objects that I've outlined in the rectangle. They are Kuiper belt objects in mean motion resonance with Neptune. What that means is that they're in a special configuration, and when let's say we're talking about the 3-2 mean motion resonance, which actually is the one that I outlined, then when Neptune goes around the sun 3 times, the Kuiper belt object will go around the sun twice. So they're in that pattern that keeps them in a special stable orbit for a long time, and I'll get to that in a few slides, why it's actually stable. And so these populations were very motivated by something called planetesimal-driven migration, which I'll also get at in the next project. But it wasn't clear that this would work, that they were reproducible with an upheaval, as I just talked about in the previous slide. So this motivated one of the projects that I'll present, in that previous work had shown that, yes, if you have an upheaval, you do populate that area shown here. But it wasn't actually, but a quantitative comparison hadn't been done because there wasn't enough data for the outer solar system yet. And so this paper was published in 2018. Then finally, we had a well-characterized survey of the outer solar system to be able to compare simulations with observations. And what I mean by well-characterized is that you pass like our simulation output to something called a survey simulator, which then allows you to debias the survey, and then you can do a better statistical comparison between your simulation and the observations. So one project that I'm presenting is with that in mind. I said that it's very computationally expensive to run the upheaval, so I'm not going to do that. Instead, I'm going to assume that that upheaval happened and populated this region right here. That red diamond is the 3-2 mean motion resonance. So if you assume that the planetesimals started in a low excited state, so circular, and just this disk right here, then the planets, they do their chaotic thing and they get to higher eccentric orbits. And in this simulation that I ran, then the blue planetesimals are the final particles. So it's these same ones, but after I think this one was like 20 million years or so. And as you see, they actually get scattered outward in a way that it populates that region. So instead, I'm not gonna run the upheaval itself. I'm going to start my simulations assuming that that area is populated. And so that way I get rid of that whole computational expense of running thousands of simulations. Instead, I can just run one really good long simulation with this initial population. And that's what I'm showing here. So the population is initialized just around that 3 to 2 mean motion resonance, which is this blue diamond. So I'm going to be showing a lot of plots that look exactly like this, which is with 7 major axes on eccentricity. And what we want to know is, can an upheaval reproduce the structure of the 3 to 2 mean motion resonance? Remember I said that, yes, it had been shown that you can populate them, but an actual comparison for specific resonance had not been done yet. And this is work that I did with some undergrads that I mentored a few years ago. And yeah, so you check which ones are in resonance, and those are the ones in blue. So you run that simulation for 4.5 billion years. And over time, you'll see that the green objects, yes?
Can you describe a little bit more detail about your simulations? Are you doing an Nbody with, say, 5 planets and then treating everything else as contributing nothing except just?
Yeah, that's a great question. Yeah, so in these Nbody simulations, we have the 4 giant planets that we have today. And they start at very similar orbits than they are today. And so the assumption is that the upheaval happened and the planets got to where they are now. And in that same time scale, this region got populated. And one thing about these simulations that is very common for the work that we do here is that the particles are massless. So they're not interacting with each other, which is fine because compared to the masses of the planets and their own gravitational interactions, that's a correct assumption, or it's a sufficient assumption for the work that we're doing. Does that answer?
Yes, it does. Are you being clever about the way that you integrate the planets? Are you using conjugate Hamiltonian variables and that sort of thing?
Not for this one, but we will get to one where I'm more clever. Meaning there's some tricks, you know? But no, in this one, they're actually just doing their real thing. Yeah. So yeah, the planets are just evolving in the way they are today. And over time, just from those gravitational interactions, which the planets are not super close to these particles, like Neptune is at 30 AU, so, you know, somewhere over here. Just by those interactions, these particles are sculpted away, and the green ones are the non-resonant ones, so eventually they're gone. And then at the end, you are left with some resonant objects that are here in blue. And remember I said at some point, I think I said that it's a stable configuration, and that is shown here because these particles that are like above this region are all crossing Neptune's orbit. And you would think if you're crossing Neptune's orbit, then you're going to get kicked out of the system. But if you are in mean motion resonance, you can actually remain stable for 4 billion years. And so that's a very special configuration for that reason. And then some of the low eccentricity ones remain as well. So now that we have the end of the simulation, we can compare this to observations. And I did that by comparing the simulation output with the outer solar system survey, which is that plot that I showed earlier, the data that I showed using the survey simulator. And we compare using the Kolmogorov-Smirnov test, which what that does is that you get the cumulative distribution function of your simulation data or simulation output and the data and compare those distributions, and you look at how similar they are. If they're very different, then you will say, well, actually this model does not actually reproduce the same configuration, so this model does not work. If they're similar, then you can say that there is good agreement, which is what we got. Actually, they were similar enough that we cannot deny that this model would not have occurred. And so something that I like to say with the KS test is that statisticians, you know, would be proud for me to clarify that it's not that we're saying it likely happened, but it's the opposite of the double negative, that we cannot deny that it did not happen, which I know is confusing, but that's like the real statistics way. And given that these results were very promising, something that I look forward to doing in the future is doing a similar analysis where this one here is the 3-2, but now we can do that same, use that same model to look at the other mean motion resonances that are beyond the 3-2. And if they work, then we have a self-consistent story for reproducing all of these mean motion resonances, where so far that hasn't been done. And the reason why is because the data just hasn't been available. So with LSST, that will be possible because we're gonna get up, or not up to, more than 10 times more data than we have now. And that's a huge, amount for this work. So it's very exciting. And again, just to clarify, the blue here is assuming that upheaval happened. So with that in mind, then we can compare, do the eccentricity distributions actually match this model? And that will be a really strong constraint. Even if they don't reproduce all the structure, looking at the eccentricity will be important. Okay, so now moving on to a different model. I talked about a gravitational upheaval, and I alluded to a planetesimal-driven migration that populates the mean motion resonances very efficiently. And I'm going to show you that in this simulation. So this is where I get clever. How the planets migrate is through angular momentum exchange with the other planetesimals that are present. That moves the objects around, and eventually they migrate. But I talked about how expensive it is to even do chaotic simulations. That introduces a lot more chaos. So it gets very difficult to model that and actually get a really good simulation in the end. Or also it takes like a long time to run. And so what I do here is that I'm not actually, so what I'm going to show you is that the planets are migrating due to planetesimals, but I'm not actually modeling the planetesimals. Instead, I'm forcing the planets to move in a way as if the planetesimals were there. And that is like a trick, but it's also well studied that is how they would migrate anyway. So it's just a nice simplification. So yes, what I'm going to show you now is the planets migrating, and Neptune is this last one right here. So as you see, as it's moving outward, these particles are being caught into mean motion resonance very efficiently. Like, it's very satisfying to see. And so that's very well motivated for why we have those mean motion resonances in the first place. But one downside to this model is that it overpopulates the resonances compared to the observations. So that means that you have to include more than just like a simple low eccentricity disk. And so what the next project that I'm going to present is talking about how, yes, if Neptune migrates out smoothly, then objects are caught into mean motion resonance, but it's actually not as smooth as we think. I mentioned that they are interacting with planetesimals, and so that introduces a lot of noise. So many of us have studied like Brownian motion in a physics or math class, I don't remember at this point, but it's like a random walk. It's a diffusive process. I think that is more recent in our grad history. And that models the Neptune's random walk very well, actually. So I did a little cartoon to show that. What I'm showing you here is the star and then some planetesimals Neptune. And it might migrate outward, but then it might go back as well, and forward and back. And so in this random walk, depending on how fast it happens or how long it occurs for, then that will affect the objects that are in mean motion resonance. So even though, oops, wrong way, sorry. Even though in this simulation, I show you how easily they got caught, they can also get lost from that resonance, and that helps answer the question of like, well, this model overpopulates them. And so with this, then you actually get objects that are lost from that configuration. And the main result of this paper was that the loss across mean motion resonances is not constant. And since it's not constant, then that is a very good signature, or like an obvious signature to compare to observations. So I'll walk you through this plot. What we did.
Before you go there, I have a question about the random walk. Do you actually calculate the fluctuations in Neptune's orbit, or do you assume it's a random walk with a probability of going left and right step size?
Yeah, it's modeled with like a Poisson distribution, and it is assumed that it's doing the random walk given the angular momentum exchange. And so as the planet exchanges the angular momentum with the planetesimals, the planet then gets like an extra impulse back on its orbit, which then pushes it around. So that's how we model it.
Do you calculate these impulses, or do you model them? That's my question.
We're calculating them.
Yes.
Yeah.
So you have the planetesimal distribution, that gives it an impulse to Neptune, and it changes its orbit, and then you use that new orbit to calculate the
Yeah, so this work is mostly an analytical model. The only simulations that I ran for this was to confirm that the analytical model was actually correct, or that it was sufficient.
So how do you analytically calculate the torque on Neptune? That's my question. Or do you do that by counting up the planetesimals, or from the distribution, the radial distribution of planetesimals?
Yeah, maybe I'm not understanding, but I will try to answer. So given the like surface density of the disk and how it interacts with the large planetesimals, that's how we, that goes into the equations to calculate the impulse that the planet receives. Is that helpful?
So I'll have to follow up.
Okay, yeah, thanks. So yeah, so one of the main results for this work was that there is a pattern that we can distinguish between how these mean motion resonances lose Kuiper belt objects. And what I'm showing here is the comparison of my work to the observed estimated populations of the Kuiper belt, or in certain mean motion resonance. So that's in light blue. The light blue, and I'll talk about the two different panels for now, but in a little bit. But the light blue is the population estimates due to observations, and the dark blue circles are the population that I calculated given some loss mechanism, which in this case, it is a surface density with 2,000 Pluto-sized planetesimals. And then you assume an initial distribution of how many objects were there initially, and you apply that, and then you can compare to the observations. And so it's not a perfect fit, of course, like every dot does not lie within the range of the observed population, but we still get a pattern, and some of them do fit. And so that's promising to be able to compare, again, back to LSST. When LSST gives us more data, there are huge error bars in these plots. And also they'll be able to constrain the eccentricity of the objects, which goes into my calculation. So while it doesn't fit perfectly now, there are a lot of uncertainties that can go in there to compare more rigorously in the future when we have more data. And the top panel was assuming an initial population given in a gravitational upheaval, and the bottom panel is assuming a population given only planetesimal-driven migration. So that's the difference between those. So just to summarize those two projects, this is alluding to the future. Again, with LSST, we'll be able to distinguish this pattern, but there's also the other pattern with the gravitational upheaval. So depending on what data we receive, we can distinguish between which model leaves the most, or which one more strongly imprints its effect onto the distribution of the Kuiper belt. So that's very exciting to do in the future. Okay, moving on to the last solar system project. So I talked about orbital distributions, and that was just diameter, axis, and eccentricity, and slightly inclination, but not so much. But not only is that apparent in this outer solar system, there's actually two distinct surface colors as well. And what that is by looking at the color of the objects, like in the B minus R, R minus G, etc. Sorry, I'm not the observer. I think those are the filters. And the thing to get from this plot is that there's clearly two populations. They're not exactly like there are some red ones on top and some in the bottom, but the majority of the red objects cluster in the bottom. And for the purpose of this talk, we'll just say that those are redder they have a range of colors, but we'll just say those are redder. So this is eccentricity and that's inclination on top. And then the ones that are higher inclination tend to be bluer. So those are the black objects. And with that in mind, and this is within this major axis region. And so with that in mind, that's something that is very interesting to compare models to think about, well, why do they have different surface colors? That points at will possibly be ones that are low eccentricity, low inclination, might have been born there, and therefore have this certain color, whereas the other objects might have gotten excited and then pushed into that region later. And that's what they propose in this paper. So when you look at the distribution of the objects and the edge on disk, then you assume that maybe they're calling these red. Sorry, the way people call the colors varies between papers, but anyway, but for the purposes of talk, these are bluer, okay? And so the idea is that they would have been born in this region, whereas the low inclination, the red ones that were in the other plot were in that region over there. And this motivates this next project that I'm going to talk about, which is work in progress, which looks at the 2-to-1 resonance, which is just exterior to that region that I mentioned earlier with the cold, it's called the cold classicals, but the redder and the bluer objects. And the 2-to-1 is right exterior to it. And so how we can take advantage to that is that as the 2-to-1 would have migrated outward, then it would have caught objects from this region. And then we can compare the color data of the objects in the 2-to-1 to the ones in the observations to simulations that I ran to be able to distinguish, well, how much migration did occur. So I guess that's showing that again in this plot. So I mentioned there are different colors. The 2-to-1 is going to go out, and some of those will be the redder ones that are caught from this lower inclination, lower eccentricity region. And so the work that I'm working on now is in running various migration histories to be able to distinguish, well, did Neptune migrate 5 AU or 3 AU or 7 AU? And was it for 10 million years or 20 million years and so on? Or was Neptune eccentric and therefore I'm going to dampen its eccentricity? And so there are various models to run here. And we're going to use the colors to be able to distinguish, because I'll look at the fraction that I caught in my simulations from that region and then compare that to the fraction that is observed that are the redder colors. And I'm going to show a simple simulation to show that point here. And it's the same thing that I explained, so I'll just let it run. Oh, I have to click it. Okay. So the diamonds are the simulated particles, and the purple line is moving outward, and it clearly catches objects from this original location. And then the black circles are some of the data. So again, that will be compared to the data to distinguish between various models. And some of this work I published, like the first part of it, which is, first of all, in creating or in modifying the Nbody code that I use, which is rebound, to be more clever, back to that point, is that I'm allowing myself and the users of this code to modify the planetary orbits in any way that they want. And that's dangerous, right? We don't want to do some crazy stuff, but that will actually make it more easier to model various physical dynamical processes that they should be well studied. And so when used, what is it that Spider-Man, what is it? With great responsibility. Thank you, yes. Right, yes, with great power comes great responsibility. So that is the motto of that code, is use it efficiently, and you can evolve the planets however you want, but as long as you do it with a way that's physically motivated, then you should be good to go. So I will use that code to run various migration models for this project. Okay, so that's the summary for the solar system. I still have the EUMIC part, which is like 10 minutes. I think I have time. So in summary, what I showed is that the 3-2 mean motion resonance orbital structure can be reproduced by gravitational upheaval. And that leaves a lot of room to further this work in the future with LSST. And Neptune's random walk is noisy enough to produce a distinguished relative population pattern across the various mean motion resonances. And the colors of the Kuiper belt offer a unique opportunity to constrain migration models. And the future forward-looking part is, again, that LSST will deliver 10 times more data. And so we'll have a lot more data for the small bodies in the outer solar system, and that will help us make stronger constraints for what model could have occurred in our solar system. Okay, so now part 2 is using the skills that I gained with, working in the solar system and running Nbody simulations and analytical modeling. I'm now running simulations to understand some interesting structure in the EUMIC debris disk. So this, the EUMIC star is an M-dwarf star. It's like 20-something million years old, and it has a very interesting disk. It has some interesting dust clouds that are above the midplane. I'm circling to here. Others are technically in here somewhere, but they're just harder to see. And what's interesting about this is that they're only on the one side of the disk, and they're moving outward. So that's 1 year, next year, and another year. So within 3 years, they've moved outward enough to not be within that oval anymore. And that's very interesting and unique to the system, because we might, see changes in debris disk structure over millions of years, but you don't really see it in yearly timescales. So this is a unique opportunity to think about what kind of dynamical process is happening here, and is it a planet or not? And this, I should say, has only been observed in the scattered light images, so in the sub-micron, 1 micron range. And there are 5 of them. The most clear ones are A and B, but the other 3 are in there as well. And this points to a periodicity. The fact that there are 5 and they look to be somewhat sequentially separated by a similar distance tells us that maybe there's some periodicity occurring with them. So this project that I'll present is looking at what dynamical process can produce the periodic clouds that are on one side of the disk and that are moving outward at high speeds. So work has been done to try and explain this structure. There has been work alluding to a collision that occurred between maybe some large planetesimals, and then due to a massive amount of dust in one region, that is periodically being ejected in a way that shows up in the observations. Or there are other methods with a parent body or a planet, but it hasn't been done to, the model that I will present has not been done yet, and with Nbody simulations as well. So the way that we're explaining this is with an inclined eccentric planet, and the debris disk is exterior to that planet. I should say also that this planet that I'm proposing has not been found. It is likely hidden behind all the dust and is larger than the other planets that have been detected. Every planet confirmed so far is interior to this planet. So the idea is that because this planet is inclined and eccentric, then it'll go around and kick up dust particles when it reaches apocenter, which is when it's closest to the dust here. And when it does that, then you get a little puff, a little cloud of dust above the midplane. But that's not enough to compare or to match the observations, because the dust clouds are moving outward as well. So we motivate that they're moving outward because the stellar wind then pushes these dust clouds out. But it doesn't push out the particles that are in the midplane in the same way, because it reaches a height that is high enough that it's no longer being self-shielded by the rest of the material. And so that explains why possibly it's also only seen in the scattered light images. Maybe only these grains have a scale height that allows this to happen. And remember, I said that there are 5 of them, and they are periodic. Some previous work has constrained that maybe that they're being ejected every 7 to 10 years. So that constraint then I use to be the period of my planet that I'm modeling as well, because then every time it approaches the debris disk, then it'll eject the dust as well. So that we see that happen over and over again, and a new dust cloud gets ejected. And there are many parameters here to play around with. There's some constraints in the literature, but a lot of it is actually a large free parameter space, which makes it complicated, but I've narrowed it down to some amount. So the parameters that really matter in this model are the planet mass, which is actually constrained by what JWST can now observe. So the mass that I have proposed is still likely not detectable with JWST. And then a planet inclination, its eccentricity, and the planet period, which is constrained by the periodicity of the clouds. The disk inner edge, the stellar wind, the force, so the stellar wind force, how large is it? The mass of the star is mostly constrained. And then the scale height of the disk, which is the parameter that I plug into my code to say, once the particles are above this height, then the stellar wind pushes them out. And I've narrowed it down to some values, both by running various simulations, but also with an MCMC to find which parameters produce particles with trajectories that best fit the velocity data. And sorry, the writing is small here, but really this is just to show that there is actually some constraints. This is very degenerate, but by using the parameters that are found from this MCMC, I ran a new large scale simulation. And I'm gonna compare my movie. I zoomed in so that I would actually compare to the observations in the same kind of dimensions. So the observations are on top, and I'm starting this movie at 100 years. So some particles have already been emitted, and the blue circle at the very end is the planet. So you'll see how it's coming in and out of the frame. And so what I'm showing here, I guess you're not seeing the right side. I should have shown you the right side so you believe me that none are getting emitted on the right. I didn't think about that. I wanted to compare to the observations. But anyways, as you see, we are actually getting clumps. And the yellow lines here are showing like what would be the disk to compare to the observations. So they would still be like right above that yellow line. And something interesting about this specific simulation is that while the velocities are actually better for fitting the data, there are some like tails that you see at the top that are not found in the observation. So this is also in prep. I'm almost finishing the project, but there might be more work to think about how I can incline the disk to possibly show why they're there, or maybe they wouldn't be bright enough for the sake of comparing to the observations. And the way that I'm doing this movie is that I ran an Nbody simulations with several millions, like 20 million particles, I think. And then it's just a density map to be able to compare with how many particles are present at given locations to compare to the observations. So in summary, I'm gonna leave many of the plots that I showed in this talk. For the solar system, I talked about constraints for what kind of migration could have occurred with the giant planets. And I talked about a planetesimal-driven migration and upheaval. And I think we're at a point where it's not an either or situation, but a combination of both and possibly other type of migration as well. And so I'm really excited with LSST that we'll actually be able to answer many more questions. And we might even get so much data that then that helps us create more questions as to like why that looks the way that it does. So that's exciting. And then with the EUMIC disk, yeah, still playing around with really matching the observations, but it looks promising so far. And it fits the velocity data, which is good. So yeah, that's it.
And I don't see clouds on the right side.
Oh, right. Thanks. Yeah, this one is right on the edge. And one thing that I didn't say is that in a newer paper, they thought that they saw stuff on the right side. That was like the 2018 paper, I think. But it hasn't been followed up yet, so it's not clear to me if they actually saw a clump or it was like a, I don't know, some observer anomaly thing at that point. But if they do have clumps on the right as well, then I honestly could like rotate this disc in a way to make them appear because they're being ejected from both sides. So that would be exciting.
All right, so I wonder if before we lead into questions, if everybody could turn to their neighbor and talk for a minute about Arcelia's talk, and then we'll ask questions. Go. Yeah. Hello. All right, thank you. Now everybody should please stop talking. Okay, any questions?
I have a really basic question. This is not my field at all. You mentioned the whole like hyperbolic object versus Transneptunian object. Is there like any difference between those two terms? Or
Yeah.
is it like two different communities?
No, that's a fair question. So I looked this up like when I gave my master's talk, actually, so I am well prepared for that. It turns out that the Kuiper belt, I think, is technically stops at like 50 AU or so, because whenever that was named, that might have been as far as they knew objects actually existed. I don't know the actual number. And so that became the Kuiper belt, right? But Transneptunian is technically anything after Neptune. But it seems that a lot of people are using TNO now because we know that there is so much more out here, that it's not just like random distributions, but like there are objects with structure here.
So
And then the Oort cloud is like way further away.
yeah. So as the point is like the Kuiper belt isn't actually a belt. It's just kind of going or it is.
Yeah, kind of. I mean, technically there is an end and then it becomes the Oort cloud, but yeah.
Thank you.
Renata?
Yes, I was wondering, with the gravitational upheaval versus the planetesimal-driven migration, mean motion resonance plot, what would the plot look like if you didn't have this random walk depopulation of the various resonances? Like, are they all populated equally, or like it looks like the gravitational upheaval actually is able to scatter things out more, which is why we're seeing like those things on the top compared to the more smooth migration. So
yeah.
how would it look like?
That is a great question. So I don't actually think that they get populated equally. The movie that I showed is not long enough. Maybe it's not worth going to it. I'm gonna try, I guess. This movie is not long enough, but I did go up to 60 AU, and then I think in this simulation, when you just migrate Neptune smoothly, the 5-to-2 population is populated more than the 3-to-2, which has not been observed. So it still wouldn't be equal, but that still wouldn't be enough to have a good agreement with the current population estimates. And you're right about the, sorry, that, I'll just leave it here. Oh, I didn't know that this was on, my bad. That the population estimates do actually seem to go up anyway, which matches this. But I think that's also a factor of like more recent scattering from Neptune. That doesn't necessarily mean that there was an upheaval, but that, you know, the upheaval would have happened billions of years ago. And in those billions of years, like scattering can still have happened with the current orbits of Neptune specifically. Like Neptune scatters objects in some perihelion distance that would go like this. But that does help that model too. But it doesn't mean that that happened. Does that get to?
Yeah. Okay. I was also wondering, sorry, like physically, what happens when you get caught into resonance? Does that like cause an eccentricity excitation, or is that more like more eccentric things are able to survive better because they're like protected by this resonance?
Yeah, that's a good question. It is true that they are protected, but there is a mechanism that actually excites them. I think it has to do with like their interaction. Would I have something that show this? Probably not. As the Kuiper belt objects are interacting with Neptune, actually I'm gonna draw. So the star is right here, let's say Neptune's right here, and Neptune is somewhat circular, and the Kuiper belt object would, eventually become a very eccentric orbit. And as their perihelion distance, which as you go up, it's lower, gets in this region, then Neptune interacts with the object, pushing it in a more eccentric way. So that's why they're going up. And then they're protected because of the push.
I'm still there, so I'm interested in astro. And they say it's a multi-object, how is this kind of time dependent?
Like in short time scales?
Yeah.
Yeah, I remember reading a paper that I haven't found since that day, and I'm so sad. But it in the discussion, it said, and so, like whatever debris disk might actually be, comparable to the interesting short time scale evolution of the EUMIC anyway. And I haven't found it since that day. So there might be at least one more. I just can't tell you which one.
Yeah, if any other object, like if this host type different, spectral that was or different, anything different, it's just see the difference.
I see. Yeah. And there are a lot of different things. Like that's interesting because it's short time scale evolution, but there are warps. I showed a plot earlier with like the big collage. There are very interesting debris disk structures that are warps or a double disk, actually. That is also interesting. That maybe it's an inclined planet that's like causing material to follow the plane of the planet, not the plane of the star. So those are other interesting structures as well. Yeah.
I had a question following up on Yuda's question. There are very few observational constraints on the stellar wind of most young and dwarf stars, actually pretty much any and dwarf stars. And so it would be really nice to have a new way to constrain the stellar wind properties. And so if you take our uncertainties on all the other parameters you showed, and when you're modeling this planet puffing out these features, that should provide some kind of constraint and uncertainty estimate for the stellar wind. And I would wonder what that might look like.
Yeah, that's a great question. And Zach and I kind of talked about that earlier. Okay. So yes, so I didn't say the exact parameters, but in that movie that I showed, the beta, which is like the stellar wind force or the blowout force over the gravitational force, is 1.7, which is low. And if I made it larger, then they would move too fast. And so maybe what I was telling Zach is that tells you something about I think like the porosity and other factors of the dust grain itself go into the stellar wind force calculation. And so it doesn't mean that the stellar wind necessarily is lower for these, but that they are being affected differently. So that's what
I wonder if it could have something to do with that, though, if you have like overlying magnetic fields that are entrapping a lot of these accelerated particles, it might be lower once you get out to the orbits of the disk.
Yeah, I definitely don't think about magnetic fields in this, but that is true. Yeah. Yeah, that's okay. Yes.
I was just curious that planet, I'm wondering, I didn't see the exact values of the average so far.
Right.
Is there a way that you could confirm whether or not those predictions?
Yeah, right. I forgot to say them out loud. So the planet is at between 3 and 4 AU, and the debris disk inner edge, which is the only part that I modeled. I didn't model like the full extended disk, starts at about 5.5 AU. And so, yes, to answer your question, yes, there is a parameter space that a planet just cannot be at, which can be found with Gaia, I think. Gaia can tell us like how massive a planet would we be able to detect. JWST has like there's this paper by Kellen Lawson, I think it's 2023 or 2024, where they have a really nice figure showing like where in semi-major axis and mass space would you be able to detect the planet with JWST if it was there. So then that gives another constraint. I think there's at least another, the RV method. So I think one thing about this system, and correct me if I'm wrong, anyone, because it's so active, it's really hard to actually find planets with the RV method. But given that at least one has been found, or then found after it was transited, I forget what was the actual thing, then that would give another constraint as to where can the planet be. Yeah, and you made me think of another thing that I didn't say. So the debris disk inner edge that I modeled is at 5.5 AU or so. And it's not well constrained like where the debris disk inner edge actually is. Like I think within 5 sigma or something like that, it could be at 5 AU. Some people favor 15 or 20, I forget the details. Yeah.
All right, we should. Thank you.
Thank you all.
So thanks. I wanted to follow up.
Yeah.
My name's Larry Esposito. I wanted to follow up